minus 10, 9, 8, 7.
Wow. What a day. We have seen so many interesting concepts. We've learned that humanity may at one point colonize the entire universe. We've seen that we might be flying to asteroids to harvest them. We've learned about artificial organs that we might use to replace parts in us. We also learned this very, very fact. This is my date, or I will die. But leading a so inspiring life, having the ability to talk to all these interesting people, really, I do not want to, ever. So how to go about it? Well, I need to build a replacement me. And being a roboticist, I need to go analytical about this. And first, what is me from a roboticist's view? So obviously, I do have a body, an embodiment. I can see it right here. It's a very good mean to change my position in space. It's also good to interact with the environment, so I can press these buttons. It contains sensors and motors, or muscles. It allows me to move. It allows me to perceive, for example, this bright light up there. And it provides the living conditions for my brain to exist, for my controller, for my computer. On the other side, we have the controller, the brain, the intelligence. It processes these sensory inputs, it makes sense of them, and then it generates motion commands. What should my body be doing in order to create new sensory stimuli? And it reasons about the world, builds internal models, and so on. So we have a very distinct two-thing view, or at least that's how we thought. In robotics, this has been a lot along the case. We build robots, and then we try to figure out how to control them. In artificial intelligence, this kind of thinking basically led to a lot of very, very interesting discoveries. But it did not bring us robots that can interact with their environment in an easy way. Every one of you is better at grabbing a random bottle than the best robots in the world. Why is this? It's because the body cannot be viewed separately from the control. And I proved this in a very, very simple example to you. So we see this very cute little robot rolling over the table. And a very different robot, more like a seal, robbing over there. And this one is crazy. It's called Crazy Bird, for that sake. It can even rotate. Now, what's the control? What's the brain behind this? And as you see, that's it. It's just rotating motors. The whole range of interesting behavior was not a result of the good control, because that was pretty stupid, but it was a result from the materials, from how these robots have been built, how they've been embodied, and how they interacted with their environment. Would I take these robots and throw them into water or sand, I would see very different behavior. So how do we go about it? How do we create robots that basically adhere to this principle? Well, we built them. We try to understand nature and robotics and how we interact with things by building robots. So let's go back to building a replacement me. I do consist of several parts. I do have a brain. I do have a body. We go back to that separation. And on the other side, we have technology. We do have very able and fast computers, and we do have very able and fast robots. But they're very unlike me. They are hard, and if I go in their way, I'll be dead. So maybe we want to find something in between that takes the best of both of these worlds. So let's look at bodies first. A few years ago, in 2007, this lab was being built. It's a very nice robot. It is built out of polymorph. Polymorph is a polymer that you can shape by hand. You basically use a hot air gun, and you can change its shape. While this is a very nice way of building a robot, it's also a very artistic way, it took a long time. So the engineer that built it took about 3 years to build it. Now, we as scientists, we wanted data, we wanted to control it, we wanted to work with this very new kind of robot, because this robot has muscles instead of motors in the joint. And we learned basically, okay, maybe we had to build it a bit more controlled, so we can actually think about controlling it. So the next version was being done. It was still made of polymer, it's still basically built by hand, but it was using better motors so we could get, and better sensors so we could get a better model. But still, it took a very long time. So we thought, okay, well, let's go the engineering way then. And we designed the robot on the PC. As you do nowadays, every car is basically designed on the PC. And we use modern fabrication techniques such as 3D printing. So eventually, this robot was done. And we were convinced, okay, now we have a very good way of building this new kind of musculoskeletal robots. But we need to talk about it. How do we make it talk about it? Well, we need a messenger, a robot that people can relate to. This arm would not have gotten me here. It would have gotten certain interesting publications, but it's not something we people relate to. We want something cute, we want something friendly, and that's what we did. One might argue about friendly. We replaced the head in the process. But basically, within 9 months, we tried to build a full humanoid robot with legs and arms and everything, based on these principles, and with a lot of help from industry and friendly people and engineers from the lab and so on. So after a while, we had a complete construction at the PC. And that's a very dangerous one, because here he is standing, which you cannot do in real life. So we had to assemble it. And I wish it was that fast. So this is about the course of 2 days, a bit more. And it was just a torso. But eventually it was done. Now the question is this a good messenger? Does it do its job? Do people talk about it? So it was exhibited at the Robots on Tour. This was the 25th anniversary of the Laboratory of Artificial Intelligence in Zurich. And boy, it did. So people were queuing up to 3.5 hours, which is also a part of our mistake. But nonetheless, a lot of people came. There was a huge media success, so we were covered by all kinds of magazines. We got to travel a lot. For example, we've been to China. Here you see Roboy in Shanghai at the Science and Technology Museum in a wheelchair. And it's in a wheelchair because we did a cooperation with a local laboratory that developed a robotic wheelchair that can basically guide you safely through an exhibition if there are people standing around. And Roboy cannot do it, he can only sit right now. So we have a very nice system to basically show around, this is a new kind of body. But I also have brains. So how do we go about it? How do we basically build controllers that are closer to biology? Luckily, our laboratory is part of the Human Brain Project. It's a huge effort from the European Union, funded with a lot of money, to basically better understand our brain. And one of the sub-projects, that's divided in 12 of them, is neurorobotics. So what is this about? What you see here is the cortical column simulation. It's a very, very small part of a brain. It's about 1 cubic millimeter. And this is simulated on a cluster. It's extremely complex and thus not usable for robots, because robots have to interact with the world in real time. If I get sensory input and I get the output 3 days later, probably not ideal. So there are simplified models of how neurons work. This is a 200,000 neuron simulation of a mouse brain. And you can see it's spiking nicely, and the spikes are traveling through the brain. It's not doing anything useful at this point, but it looks nice. But more importantly, the neural models are much simpler, and we can use them to calculate in real time. But still, this is run on a large PC, and what we need is something mobile, something smaller. So luckily, at the University of Manchester, a neuromorphic hardware is being developed. It's a hardware that makes it very easy to create large neural networks that spike. And this is the smallest version of it. It has about 64,000 neurons that we can simulate on this hardware. It's way less than an ant, so we cannot do that much yet. But luckily, we have larger boards, up to 768,000, so it's almost a bee. But it's a human brain project, right? And we want to build humans, so we got to go further. So we use a lot of these boards interconnected to each one, so it's just already 9 million neurons. The mouse has 70 million, so we're still far away from where you need to go. So why not take 10 of these and put them in a rack? Gives us 90 million. It's a bit more than a mouse. A rat has 200 million. Catching. Now we take 10 of these racks, and that's the largest system that is being planned right now. It has about 1 billion neurons to be simulated. And, well, we humans have over 20 billion neurons in our cortical network. It's a bit a long way still. So where we are right now, we have this modular system where you can basically arbitrarily assemble your robots. This is the simplest model that you'll see. It's just 2 bones and a joint in between and 2 muscles, and we can do a lot of interesting things. For example, when you throw a ball, what you're doing is basically you're contracting the muscles in your frontal thorax and in your back, and then you only release the ones in the back. So you stored energy in your muscles. And it's something we can show here, we can do here, and we connect it to these artificial neural networks to find controllers that are based on neural networks that basically allow us to use these features. So there we're at the very beginning. If I showed you a video of this system, it wouldn't be very interesting. It's just tickering a bit. But in simulation, this is much easier. So, for example, this is a mouse. This was easy. And its whole skin is mapped onto a sensosomatic cortex. So basically, it's a part of a brain, and whenever a part of the surface is stimulated, it turns up white. And you can see here how the stick is basically, it's a very small part of that violet thing further down. It's creating an excitation that we can basically see in the neural patterns. So with that, we have an interesting way of building brains that's somewhere in between what computers are and what our brain does. We have an interesting way of building bodies, which is somewhere in between of what classical robots are when our body is. And with this, we're entering a new space, and it's basically new because we don't know where we're going. But it's very exciting, and I hope we'll see much more people there. Thank you.